This afternoon's speakers are incredible in this room, as is in the other room. Just so much to learn, and the day's going great so far. So just a quick reminder, after each talk, you'll see a QR code flash up. Really appreciate your feedback on sessions. And without further ado, we're going to introduce Hamza to stage. Hamza is principal in the industry solutions team at MongoDB, looking after manufacturing and IoT use cases. Prior to joining MongoDB, he was working at Ernst & Young Canada as a senior manager, looking after digital operations consultancy practice. Since earning his PhD, Hamza has spent most of his career enabling smart and connected factories for multiple manufacturing clients. In 2020 to 21, he helped establish a multi-year strategic roadmap for Singapore's smart supply chain initiatives. Please give a round of applause and welcome Hamza to the stage.
Thank you, Chuck. Hi, everyone. I hope everyone is enjoying themselves. A good lunch. My name is Hamza. I joined MongoDB recently as a principal in industry solutions team. I look after manufacturing and IoT and industrial IoT use cases. And I'm very excited to be here presenting to all of you. This is my first .local, so very happy to be here. And our talk today is actually going to talk about taking these abstract concepts such as Industry 4.0, digital manufacturing, digital twins, and we'll see how we can actually implement them using MongoDB Atlas technology. And I hope you'll find this presentation relevant and useful in your work. Okay. So I've put together a little agenda. We will start by giving a high-level overview of what Industry 4.0 is, what our reference architecture is, and then I'll introduce this concept of asset administration shells and how they form the basis of a digital twin for a manufacturing asset. Afterwards, we'll create a digital twin of a robot using our Smart Factory testbed as an example. Okay, so with that, let's get started. So let's start with some basic definitions. So Industry 4.0, or the fourth industrial revolution, is actually a concept. It's a concept that when applied correctly, it enables digital manufacturing via cyber-physical systems. And cyber-physical systems are nothing more than computers running some software that take data from your equipment, from the machines on the manufacturing facility, store them, analyze them, and help you visualize the results of the analysis. So manufacturing companies start their Industry 4.0 journey by doing digitization, which is just the process of converting analog data to digital form. For example, if you're walking around a factory floor, you're capturing some safety trigger information on a piece of paper, you convert it into Excel form and use Excel from moving forwards, right? So the next step after that is digitalization, which is to take that digital technology that you have just replaced your analog technology with and actually use it in your existing business processes. So for example, for maintenance processes, for HSE processes, you start to use digital technology more and more. And then finally, we have digital manufacturing, which is the process of actually using this Industry 4.0 concept, using cyber-physical system devices, install them on your shop floor, get all the data out, and not just use these technologies in existing processes, but also use it to create new experiences for your workforce and also for your customers as well. So creating new business processes, new customer experiences digitally is what digital manufacturing is. And this term, I have to say, has been around for quite a while. So I want to differentiate between what's possible today and what is new. So we know that network technologies are stable, they are available. Companies are even looking into private 5G networks to have data stream from their devices into one central platform and analyze there. Cloud computing is stable. There are a lot of industrial IoT platforms available in the market, competing with each other. And then machines and new robots that manufacturing companies buy, they come with inbuilt sensors, they come with inbuilt IoT gateways and so on. So that's all there. What's actually new and exciting is taking all of these technologies together and using them in a way that you can create a uniform and standardized data models or model your assets or equipment in a standardized way. So that will help not just with scalability, but also allow you to enable like information exchange between these different assets. And once you do that, right, that's when you actually create these digital twins of assets, which add value to the operations of manufacturing by meaningful information flow. So I use the term digital twin here. Let's define it a bit further. Nowadays, when people talk about digital twin, they're actually talking about digital shadows most of the time, or advanced digital shadows, where the physical device is sending some information to its digital shadow or to a software, and it gets analyzed, the data gets analyzed, and some notification or trigger or action is performed and then sent back to the device. But is it truly a digital twin? Because when we want to talk about digital twin, it has to be bidirectional synchronization in real time with the physical device and also with other assets on the shop floor, enabling real-time monitoring and control. So once we have these digital twins for our products, devices, workstations, machines, they can talk to each other in the software layer, and thus enabling or helping transitioning manufacturers from this old hierarchical pyramid of the factory to a new pyramid or a new model where different devices can talk to each other seamlessly, exchange information seamlessly, and that's the new smart factory model, right? So it all sounds good, but it's all theoretical, right? And so how do we get started with this? So we have to start with the reference architecture. And I'm showing a reference architecture called RAMI 4.0, Reference Architectural Model Industry 4.0, which was developed by the German Electrical and Electronic Manufacturers Association for German manufacturing industry. And what it does, it helps you create a common understanding or develop a common perspective of all the processes that are happening on the shop floor and looking at them from a digital technology lens. And in a RAMI 4.0 architecture enabled factory, the factory is actually a network of interaction between smarter products and the connected world. So it all sounds a bit abstract, and to be honest, does not really help with like anyone who wants to actually develop applications for the connected factory. So how do we make it less abstract and try to implement it? So to do that, we have to start with the cornerstone of this architecture, which is an asset. So what exactly is an asset? An asset is anything that has a unique ID and has a mechanism of sending and receiving data. So all your machines, all machine components, all products, technical drawings, supervisors, operators, job orders are all assets. And at the core of Industry 4.0 implementation, every asset's digital twin can be modeled by something called an asset administration shell. So to recap what we have seen so far, to achieve Industry 4.0, we need to start with the reference architecture. That's the first step. And our reference architecture tells us that all the items in manufacturing shop floor should be modeled as an asset. An asset administration shell is a way to model these assets. And these assets are connected to each other, and they exchange information using standard APIs. So how does an asset administration shell work? It has two parts. You have a header, and then you have a body. And the header contains information for identification, administration, and usage of the asset. And the body part contains submodels, which are actually properties of the asset. So depending on your use case, your business function requirements, you can expose relevant information from the physical device into the shell. For example, if you're making an application for maintenance services, then you can just expose things like maintenance log, technical drawings, and other manuals. If you're making application for operations, then you can include information from the sensors installed on the device. Okay. So let's try to design an asset administration shell for a computer numerical control CNC machine. So we have this machine, and we want to do the condition monitoring. We want to know when the machine is running or not. We also want to easily be able to access information regarding maintenance of the machine. So based on these requirements, I can define two submodels, condition monitoring and maintenance. And then in the body of the shell, I can put in relevant information. For example, for condition monitoring, we can put in the total number of hours that the machine was running. For maintenance submodel, we can put in information like maintenance history and logs. And then this shell can talk to other asset administration shells using this component manager, which is just a bunch of standard APIs or REST APIs that enable information exchange, right? And you may start to see how these models form the basis of a digital twin, because it contains information about the machine that is required for a particular business use case. And you don't want to make a digital twin just for the sake of it, right? You want to make a digital twin because there's a need for it in the business functions. So let's try to write that same AS that we saw in a JSON structure. And this is what it will look like. And it has to be noted that we can have many additional submodels for our machine shell. And the raw or the analyzed data can be stored in the body of this shell. And as an example, we can see here that the coolant temperature of the machine is stored here with the degree centigrade and some value, which is an important subsystem of the machine and needs to be monitored at all times. So as we all know, that any piece of data that can be represented in JSON can be natively stored in MongoDB and can easily be retrieved in a JSON structure. So MongoDB drivers take care of converting all this data into binary JSON or BSON, and then back when you are querying the database. So of course, you can use documents to model other things like time series, key values, even events as well. So that's the beauty of MongoDB, that these documents, the way it's built on, is universal, flexible, and helps you easily model your assets or machines or robots. So with this information, let's get to actually like developing digital twin of a robot. And over time, the industry solution teams uses this Smart Factory testbed, a small-scale testbed from Fisher Technic, to actually demonstrate how MongoDB can be integrated to solve digital transformation challenges of industrial IoT with this flexible, scalable, modern developer data platform. And using this small-scale factory from Fisher Technic, our team collects data. The data is sent over MQTT protocol, and then we process it in MongoDB. And it's similar to full-scale factory. There's a warehouse there. We store the incoming material. Then a robot picks up the pieces, moves it to production area, then to sorting line, and then finally outcome. And we have prepared a roughly 1-minute video to give you introduction of the model factory and how we use it. So let me just quickly play it for you so you get an idea, and then we will focus on the robot and see how we can model it as a digital twin. Let's play it. Awesome. So let's go to the next slide. So you've seen that we have a bunch of sensors in that factory. They're sending some time series information. We're also getting some acknowledgement messages from the robot and other equipment on that factory. We use it to store like that data, store it in MongoDB, and then we generate apps on top of it. So using app services and so on, we can create alert apps and so on. So this figure shows the process of our factory. So we'll focus on creating the asset administration shell of the robot, as that's the critical equipment in this whole process. If that fails, then the whole factory will fail. So for the process that we have chosen, is the one highlighted or bordered in that black box. So the robot has to move items from the warehouse to the production station. And that's what we're going to focus on. So we will achieve our goal using a series of 5 simple steps, and I'll go through each step one by one. So the first and most important step is to capture these business requirements, because that will drive the creation of our asset administration shell template. Then we will go and you start using MongoDB to actually model this data, populated data from the data coming from the actual device, and then we will visualize it. So all these steps we'll use MongoDB Atlas. So starting from the first step, business requirements capture. And the whole idea behind creating these digital twins and modeling them and as asset administration shell is to develop a scalable, flexible model that can meet Industry 4.0 requirements, right? One of the most important key performance indicator or KPI that manufacturing companies strive to achieve is overall equipment effectiveness, or OEE. And it measures the percentage of production time that is truly productive. So you take all the losses out of your daily production, like availability loss, machine is not available, it's broken, there's a downtime there. You take it out, you look at performance issues, maybe the robot is delivering times, the cycle time of the robot from point A to point B is taking longer than expected, or you take out all the quality losses as well, where some of the pieces while transportation were dropped and are damaged. So you take all that losses out, then you get an OEE value. And these formulas give us an idea of how to design our asset administration shell. So we need 2 types of information. We need the time information, total run time of the robot, what was the total planned production time that was supposed to run, what was the total stop time. We need information about the count as well, how many pieces it transferred from the warehouse to the production station, how many pieces were dropped, and how many pieces were successfully transferred, so good count versus total count. So when the product is received at a station, the controller at that station publishes an acknowledgement message through the MQTT protocol. And these messages look like this and stored in MongoDB's Atlas time series collection. In the case of our selected process, the message flow will look something like this. So first, robot will send out an acknowledgement that it has picked up a product from the warehouse. We'll receive a code 3 with a timestamp. And then the robot will send out another acknowledgement that it has successfully transported a product to the production station. It's now in the production station. And we'll receive a code equal to 7. So this is where MongoDB time series collections come in. And we all know that MongoDB automatically stores time series data in a highly optimized and compressed format, making it very easy to query data. And when you're using time series collections, MongoDB automatically creates a cluster index against data ordered by time, so you can query data with little latency. And we have also expanded the query functionalities or MongoDB query API with a set of specialized time series queries like window functions, for example. So you can take a start time and end time window and then do calculations on it. And the time series collection, and this is my favorite bit, that the time series collections sit right next to your regular collections. So you don't need a separate specialized database just to handle the time series load, and then you have to make sure that the data is synchronized between the two, and you have to add additional context in the time series database from the other database. So you can easily blend the time series data with your enterprise data. And a time series collection, creating it is very easy. It's composed of 3 components. So time series field, in our case, that field is represented by TS. Then there's a meta field or metadata, which just uniquely identifies a set of messages, and it rarely changes. So in our case, we can put a robot ID there. We can put the granularity, that how often we are expecting to receive this data as in seconds. And the time field is the only required parameter for a time series collection. So let's see how our data will look like in MongoDB. And we have the robot messages coming in as a time series. Then we have modeled our robot asset administration shell based on the business requirements that we wanted to capture. So we have two submodels in the body. One is product-related information that has properties stored in it regarding total product count, good product count, bad product count, and so on. And then we have a production submodel which has data stored with regards to time, total runtime, total stop time, and so on. And we can add additional submodels to it as well. And because MongoDB follows this document model, makes it very flexible to add more submodels without worrying about schema design. It also serves as a template, so you can apply it to other equipment, even if it's not a robot, right? And then we have a separate normal collection of overall equipment effectiveness, where we have availability, performance, quality values in percentages out of 100. And the reason why we put it as a separate collection, a modeled a separate collection, is because in the future, if you need to calculate this value or these values through a different formula, you can easily create a new collection and then do the changes there, or you can extend your submodels in the robot AAS. So the middle collection of robot AAS serves as a template to enable different use cases or business requirements. So we have modeled the data. We have the raw sensor data or acknowledgement messages coming in. Now we need to transform these raw acknowledgement messages into something that will help us calculate the final OOE percentage. So MongoDB Atlas triggers can be used here. They allow you to run server-side logic in response to database events, such as an insertion that's happening or according to a schedule. And MongoDB Atlas provides two types of triggers: database triggers that respond to some document inserts or changes or deletions, and schedule triggers. So you can actually execute functions according to a predefined schedule. So we want to know what was the availability loss of the robot. We want to know what was the performance loss of the robot at the end of the shift, so that we can make improvements in the next shift, right? So we can set up a trigger that runs after every production shift at every day. So in our case, we will set up a trigger based on the production shift timing schedule. So it fires once a day, every day, at the end of the shift. And when the trigger is fired, it will run our custom function that we can write inside the trigger, and the trigger will run it. And this custom function will take the data and filter it for the day, and then it will calculate values like product counts, total runtime, and so on, and update the other collections that we have, such as AAS collection and also the OOE collection. And the formula for quality, performance, availability that we've seen before can be set up inside this custom function, therefore reducing your dependency of creating a HTTPS client outside of MongoDB Atlas and then communicating back and forth and retrieving data and then doing calculations. So that's an easy way to do it. So if I can move this. Yeah. So inside this custom trigger function, the aggregation framework can be used to transform and update values in our AAS schema. So here we show an example where how a custom function that runs an aggregation pipeline over the robot messages documents, and then updates the total product count field in the robot AAS document. So this custom function can be expanded to do other things as well, to include OOE calculations and updated OOE collection in the same manner. So the first thing that happens is we filter the documents according to the acknowledgement code. So if you're calculating total product count, we need to know how many items robot picked from the warehouse, right? So we filter it using code 3, and then for today's date. So we want to see how many messages were sent in the total production shift. And then we can, oops, sorry, just moved. Let me go back. Okay, so then we can pass these documents in the next stage and perform a count in our aggregation pipeline. And then we can project the total product count as an output. And once we have the total product count, and then we can update the value in the robot AAS collection, and we can do it for other collections as well. So how it comes all together is the robot is sending messages through a Kafka connector. As you may know, we provide Kafka source and sink connectors, and we use them in our factory testbed as well. So once the data is in, the schedule trigger runs, and it updates the other collections with the necessary data. You can have more than one trigger running if you want, or you can put all these business requirements in one trigger and do the calculations there. So of course, MongoDB provides other options as well to achieve the same outcome. There is data API that lets you read and write data with standard HTTPS requests. To use data API, all you need is a HTTPS client and a valid API key. You can easily set it up just by a few clicks. And then there are official and community supported drivers as well in many programming languages that can be used. The key point here is regardless of which option you are using, MongoDB Atlas provides inherent flexibility to the developers to build their applications. And that's the key message. So looking at our final architecture. And before that, we have to visualize this data because we have modeled it, we have done our calculations, transformed it, updated the collections. Now we have to visualize the final results, right? So MongoDB Atlas can be used here, and it's the best way to visualize MongoDB data because it's built for the document model, and visualizing JSON data is so much easier. So you can spend less time on actually creating these charts and do more time in innovation. So it's integrated with Atlas. There's no setup requirements, and you can also embed your charts using the iframe or the embedding SDK. So all you have to do is select your data source. In our case, we'll select the OE collection and drag drop the widgets inside, link them to the data source. If you want, you can adjust the size and all the colors, and you'll get a very neat dashboard within minutes. And you can set up the refresh rate, so you can have it refresh like every minute or every 5 seconds and so on if you want. So that was our step 5. And why is it not moving? Okay. So this is a complete architecture of our use case looks as shown here. And finally, to complete this digital twin implementation, we need bidirectional communication as well, which can be done through the Kafka connector, sending messages to the MQTT broker sitting in the middle, which the robot MQTT client can subscribe to, listen the messages, and perform actions as needed. So we are sending data through Kafka streams, time series collections, running triggers with custom functions, visualizing data on charts, which can be ported to a separate OE dashboard. So in summary, we understand that for manufacturers and for other industries as well, of course, innovation through the digitization of their products and services is of paramount importance. And starting on Industry 4.0 is easy, and scaling up is hard. There's a lot of cases where you start a pilot project and it works fine, but when you want to scale it, then it becomes challenging because you didn't start with standardized data model, a standardized way of modeling your assets and exposing information and talking with other assets, right? So scaling up is hard. And standardized models and templates for digital twin make it easy to implement, scale Industry 4.0 initiatives. And most importantly, MongoDB is strongly positioned to enable Industry 4.0 through the use of asset administration shell modeling. And then there's so many features you saw here today that all come together very nicely in a neat, integrated manner. And all of this can be used for different industries, not just manufacturing. So all these capabilities allow MongoDB to be in a unique position to fast track the digital transformation journey for our clients. So let us work together to realize your vision for Industry 4.0. And that should be my last slide. And I want to thank you for your time and for listening to my presentation. Please leave some feedback if you learned something new today. Your feedback matters, will help me a lot. And I think we have like 2 minutes, so if there's any other questions that I'll be happy to take. So thank you.
If anyone has any questions, there's some mics on the floor. We have a couple minutes. Also want to mention that Hamza has another talk at 2:20 in the other room. Yeah. So you can hear more from him. And I'm sure folks can find you in between sessions as well.
Yes, that one is on connected vehicles, comes with a live demo, so would be interesting. Okay.
All right. Thank you, Hamza.
Thank you.